Okay, on to section 1.2, where we'll make a little more rigorous the idea of the magnitude of a vector. Vectors have magnitude and direction, very informal. But the magnitude part we're about to make sense out of. There are settings in which vectors have neither magnitude nor direction, whatever direction means. But in Rn and in this class, vectors are going to have magnitude and direction. So if you want to think in terms of arrows and the physical approach of magnitude and direction, you're good to go. You're always good to go with that in Rn. But there are exotic vector spaces out there where the idea of magnitude, for example, doesn't make sense. They're probably not very useful vector spaces, but they're out there. So the plan in section 1.2, title of which is the norm and dot products, and it's norm that'll give us the magnitude of a vector in Rn in this section. Plan is to, again, build on your physics background maybe of thinking of vectors as having magnitudes and direction and put a clean definition on magnitude. We'll never put a clean definition on direction. That's kind of an informal idea. We'll try to elaborate on that as the sections go by. But direction is, in some sense, it's related to bases, as we'll see later on. Magnitude, we're good with magnitude. Here's the definition of magnitude right here for vectors in Rn. Definition 1.5 says that vector v have components v1 through v sub n, a vector in Rn. The norm or magnitude of vector v is, it's denoted with these look kind of like double absolute values, these little double symbols here on either side. The norm of v is the sum of the squares of the components of v square root of. So take the squares of the components, add them up, take a square root. If you like summation notation, here's an alternate version of that. That's the norm. Now this has quite the geometric interpretation. And if we're going to talk geometric interpretation, we're going to have to talk vectors in standard position. So here comes some of that. Let's actually get that definition in front of us at the same time as we talk geometric interpretation. So this actually might look a bit familiar to you. This definition is consistent with the idea of a vector in Rn in standard position, that is, with its tail at the origin, and vector with components v1 through v sub n, having then its head at the point with coordinates v1 through v sub n, the pictures that we had in the previous section. And then if we measure the distance, say, between the origin and that point, using the distance formula from Rn, here it is. If you want the distance between a point with coordinates x1 through x sub n and y1 through y sub n, 2 points in Rn, that distance is the usual thing. You're most familiar with it in R2, in the Cartesian plane, where you take a difference in first coordinate squared plus a difference in second coordinate squared and take a square root. Well, just continue through all of the coordinates of the point. That's how you measure distances in Rn. That's the Euclidean measure of distance. The proof of this then is based on the Pythagorean theorem. Pythagorean theorem is based on the parallel postulate. So all this stuff we're dealing with in Rn is Euclidean spaces, is how we define them. They satisfy Euclidean geometry. The parallel postulate holds. More informally, these are flat spaces. Einstein comes running along 120 odd years ago and thinks of gravity as a curvature of space-time and has to deal with curved spaces. All these spaces, they're flat. Whatever curve means, these ain't it. These are flat spaces. And you can tell because in a flat space, Euclidean geometry holds. We're using the Pythagorean theorem, totally based on the parallel postulate of Euclid's geometry, totally Euclidean geometry here, and flat spaces. You want to deal with curved spaces. Yeah, they're built in some sense out of these little pieces of these flat spaces. But as far as we're concerned, these spaces, they're flat. You can tell because of the way we measure distance, which is going to come out as an artifact of the way we define norm and dot products. So if we were to measure the length of that vector that had its tail at the origin and its head at this point with the coordinates, v1 through v sub n, then we'd get exactly what we had for the norm of v. So totally consistent with your experience from the past in measuring distances in Rn, or at least in R2. Take calculus 3 and you'll move into higher dimensions than 2 at least. Some properties of the norm are as follows. We'll run through a proof of one of them here in the notes. Some of the others are done later in the section and possibly as exercises. Theorem 1.2, properties of the norm, says let V and W be vectors in Rn, and let R be a scalar, an element of R, the reals. Then the norm of V is greater than or equal to 0, and the norm of V equals 0 if and only if we have the 0 vector. All right, not in the least bit surprising, right down here is the formula for the norm of a vector. Square roots are never negative. That's the meaning of the square root symbol. So the fact that norms are defined in terms of square roots is immediately going to give that the norm is greater than or equal to 0. Oh, and the only time we could get 0 out, because we've got a bunch of non-negative numbers added together, the only way we could get 0 out of the square root is by the sum being 0, and the only way that's going to occur because of the squaring is if each of the constituent pieces v1 through v sub n were 0. So that, totally unsurprising. Second property, also unsurprising, but we'll go through and establish that with a little proof here. If we take scalar r times vector v, the norm of that, that's the same as taking the absolute value of r times the norm of vector v. Let's run through proof of that. Then we'll look at the third statement. Suppose v is an Rn and r, lowercase r, is some scalar from the reals. Okay, let's establish that. The usual way, we'll write the vector in terms of components and then take one side of the equation and turn it into the other side. So let vector v have components, v1 through v sub n, as we've always done with vectors from Rn, and see what you get when you take r times vector v. That would be r times, express the vector in terms of the square brackets and its components. Okay, the definition of scalar multiplication says take this r and put it on each of those components. Definition 1.1 part 3 for the record is how scalar multiplication in Rn works. Okay, you want the norm. We'll use the definition of norm. It says take the first component, square it, plus second component, square it, and so forth. Up to the nth component, square it, add them together. That's the definition of the norm of a vector. Remember where we're going. We're trying to extract from the norm of RV, the norm of RV, absolute value of R times the norm of V. So let's do some rearranging, some properties of algebra. You know properties of algebra of numbers. We've got an R squared in each of these terms. Factor that R squared out, leaving us with a V1 squared plus V2 squared up to V sub n squared, all times the R squared parameter. That'll give us a square root of R squared and a square root of the sum of the squares of the components. Whoa, that's just the norm of V. So we get a norm of V there. Square root of R squared is not R. It's the absolute value of R. Remember, square roots are never negative. You've been exposed to this at various times in the past, I'm sure. But the square root of R squared is the absolute value of R, and that's what we were trying to show. So the norm of R times V is the absolute value of R times the norm of V. A third property, also geometrically not surprising, maybe what's slightly surprising. It takes a little while to get through proof of the triangle inequality, but we'll do it. It says the norm of v plus w is less than or equal to the norm of v plus a norm of w, v and w being any vectors from Rn. First, where's a triangle? Well, let's draw a picture of what we're up against there. All right, it says the norm of v plus w, the norm of v plus w is less than or equal to the norm of v plus the norm of w. Well, let's use the Parallelogram Law of Addition and look at vector v plus vector w. These vectors are in standard position, right? That little bold-faced zero right there is Fraley and Beauregard's way of saying these vectors are in standard position. Vector v plus vector w, parallelogram law of addition says we'll get v plus w to be the diagonal of this parallelogram. Now, the triangle inequality dealt with the length of v plus w, the length of v, and the length of w. The length of this side of that parallelogram is the norm of w. The length of, the norm of v. The length of this side of that parallelogram is the norm of w. And the length of this diagonal of the parallelogram, the diagonal is determined by v plus w, so the length is the norm of v plus w. Length and magnitude or norm of those vectors. All right, so you want to think of it like this. We're making a triangle using 3 sticks. The stick of length norm of v, stick of length norm of w, and stick of length norm of v plus w. Now the claim was in the triangle inequality was the norm of v plus w is less than or equal to the sum of the norms of the other 2 vectors. Norm of v plus w is less than or equal to norm of v plus norm of w. Okay? So if we were going to take 3 sticks, stick 1, stick 2, and stick 3, and make a triangle, I can't have like one really long stick, v plus w, and 2 little short sticks of length norm of v and norm of w. And I can't place them end to end and build a triangle because the third side's too long. That's what the triangle inequality implies. The only time you can make a triangle out of a line segment of length norm v, a line segment of length of norm w, and a line segment of this length is when any one of them is no larger than the sum of the other 2. They've chosen to list them in a particular way. This gives us a quick triangle interpretation. Because of the parallelogram law of addition of vectors, a triangle involving vector v, vector w, and vector v plus w. Oh, you ain't seen the end of the triangle inequality. We'll be doing a fair amount of stuff with the triangle inequality. You stay in math, you'll do a bunch of stuff with the triangle inequality in additional classes. Okay, so there's what it means. We're going to want to prove the triangle inequality. We'll have to establish something else first. We'll be back and we'll establish the triangle inequality. But first, a little more vocabulary. We've come really close to this idea before. It's formally defined now. A vector with norm 1 is called a unit vector. And when we have unit vectors, we usually put a little hat over them. The shift 6, the caret, is put over unit vectors, common notation. This really is a common notation, not just the Fraley and Beauregard thing. And we use that notation when we were talking standard basis vectors in the previous section. Oh, those standard basis vectors, they were all unit vectors, if you'll look back. And that's the reason we put the little caret over them then. I may have, but shouldn't have dropped the term unit vector back in the previous section since that wasn't defined. I should have talked about vectors of length 1, even though the length of a vector wasn't formally defined until we defined norm. Let's do an example. Let's look at number 8 from this section. Okay. So find a unit vector parallel to vector W, which has the opposite direction. Okay, we'll have to recall what parallel vectors were. We need to deal with the length of the vector and this opposite deal. All right, so here's the plan. We're going to take this vector W. Let's find its magnitude. If we divide vector W by its magnitude, that'll give us a vector of length 1. It'll give us a unit vector. So dividing vectors by their norm is called normalizing the vector. It turns them into unit vectors. We're thinking of vectors as things with magnitude, which is now cleanly defined, and direction, which is not so cleanly defined. But we're really just using this vector initially here for its direction by making it length 1, kind of a standard unit of measure type thing. But this process is called normalizing. So what we'll do, since they want a unit vector, we'll just take this vector, divide it by its magnitude. That'll give us a vector of length 1. That'll give us a unit vector. Then we'll deal with this opposite direction deal in terms of parallel. All right, so we'll find the norm of W. That's simply take the components of W, -2, -1, and 3, square them, add them together, take a square root, gives us a square root of 14. It's pretty common to get stuck with some irrational square roots when dealing with norms of vectors, and it's not impossible, but not common, that we'll take the sum of 3 squares and get something that's a perfect square. So it's common to get square roots that we can't get rid of, we can't simplify away when dealing with norms of vectors. Yeah, so we get square root of 14, that's the length of W. So if we'll take W and divide it by its norm, a quick technical comment, we're really taking vector W and multiplying it by 1 over its norm. Division wasn't something we really did. We multiplied vectors by scalars. Give me a little break on that verbiage. When I say divide by this number, I really mean multiply by its reciprocal. Technically, there's no such thing as division. It's multiplication by multiplicative inverses. But anywho, multiply by 1 over the square root of 14. That's scalar multiplication. We're good. You get your definition of how to deal with scalar multiplication. So here's a vector. It's a unit vector. We just normalized it, making it a unit vector. Oh, it's in the same direction as W, though. What was up with same direction and opposite direction? Vectors were parallel with the same direction if one was a positive scalar of the other. That's what we got here. That positive scalar is 1 over the square root of 14. This vector is 1 over the square root of 14 times the given vector. So those vectors are parallel with the same direction because 1 over the square root of 14 is positive. We don't want one with the same direction. We want one with the opposite direction. So we need a negative scalar. All right, well, let's just take that given vector and multiply it by -1. That won't change the magnitude. The second property of norms implies that. Multiplying by -1 changes the direction in the sense that we've used it in this setting of parallel vectors and same and opposite directions. But it doesn't change the magnitude. So multiply by -1, that gives us negative, the vector we just had. So take that negative, we're really multiplying by the scalar -1. So that scalar -1 goes inside on each of the components, giving us positive, positive, and negative in this case. And there's a vector. I guarantee it's a unit vector. Check it if you like. It's a unit vector, and it's parallel to vector W, and it has the opposite direction. Why is that exactly? It should be a negative multiple of W. Yeah, it is. It's negative 1 over the square root of 14. We did the 1 over square root of 14 part up here and the negative part down here. So this vector is a scalar multiple of W, and that scalar is negative. So it's parallel with the opposite direction of vector W. We also chose those scalars in such a way that this is a vector of length 1. So we normalized and then multiplied by a -1 to get the first unit vector part with a normalization, and then the opposite direction part with a -1. Back to the notes. Okay, next is a definition of dot product. Definition of dot product is going to be quite useful in a bunch of stuff we do. You might ask yourself, why would you want to do this? We'll motivate it here in a second. Good news is, well, it's an easy manipulation. So the dot product between vector v and vector w. So we've got vector v with components v1 through v sub n, vector w with components w1 through w sub n. The dot product indicated with, if I can highlight it, I guess I can't, that little dot right there, read v dot w. That dot product is v1 times w1 plus v2 times w2, blah, 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 plus v sub n times w sub n. Is the sum of the product of corresponding components of v and w. First off, that ain't a vector. V dot w is not a vector. It's a sum of a bunch of numbers. Then it's a number. It's a scalar, if you will. And in fact, some folks call dot product scalar product. In some settings, you may hear it referred to as an inner product as well. In chapter 3, we'll talk vector spaces, and time permitting, there's a section on inner products. But dot product is the term that's commonly used in Rn. Scalar product might be used in Rn. Inner product might be used in Rn. Inner product's usually safe for some other settings. But scalar product is a reasonable thing to call it because you take two vectors in and you get a scalar out. So you've multiplied those two vectors in some sense. In this sense defined right here. You haven't multiplied two vectors together and got another vector. We have not, and I would like to say, although it's false, and we never will do that. You don't multiply two vectors together and get a third vector. Okay, we'll do a little bit of that, but it's not a very general thing. It's a thing when we encounter it that's only valid in R3, it turns out. It's cross product if you've ever seen it. But here we're taking two vectors and manipulating them in such a way to produce a scalar. Now you might wonder, why would you want to do this? Well, here's why. Turns out, and you want to put this in your head, dot products are related to angles. Dot products, in a sense, about to be spelled out in detail, dot products tell you about the angle between two vectors. Dot products will be extremely useful, though this word doesn't make sense yet, when we do projections. We're going to do a bunch of projections in chapter 6, I think it is. I think section 6.1 is on projections. And projections are super useful things. When you take a vector and break it into components, you can do that using projections, which means you can do it using dot products. And if you've had an introduction to physics class, you'll take force vectors commonly and break them into components in different directions. So this will be totally useful stuff. Can't argue with it, it's a definition, but hopefully it's good for something. Here's what it's good for. Okay, so dot product was given as the sum of the product of the corresponding components of two vectors. All right, let's do a little geometric argument here, where we're going to draw a picture with vector v, vector w, and we're going to let angle theta be the angle between v and w. Is this a legitimate picture? Well, it is. We've got really, when we draw these vectors with their tails at a common point, if you want the geometric interpretation, we've got 3 points in the story here. We got the point that's at the tail of both vectors, the points at the head of this vector, and the point that is at the head of this vector. So those 3 points in that triangle, 3 points determine a plane. Okay, make it the plane of the computer screen here. So this is a general picture in that sense. That's true even in higher dimensions. 3 points, three non-collinear points determine a plane. That's valid. It's certainly valid in R3. You ought to believe that. That's why a tripod's got 3 legs. You can even set it down on a bumpy surface and still all 3 of the points will touch the ground. But this is a fairly general picture. even though we've just drawn it on a piece of paper, in essence. All right, but we're letting theta be the angle between V and W. We're going to talk about the length of this side, which is the norm of W, the length of this side, which is the norm of V, and the length of this, which is, say, the norm of V minus W, or the norm of W minus V. And I'm talking direction, so I'm sorry, talking distance, not direction. So whether we take V minus W or W minus V, the norms are the same. V minus W, V first, V minus W would be a vector from here to here. W minus V would be a vector from here to here, if you'll recall the pictures from the previous section. Well, anyhow, the norm is the length of this side. All right, so we want to look at this as a triangle with sides of length norm W, norm V, and norm V minus W. Is it a right triangle? Not necessarily. If theta is a right angle, then yeah, I guess it could be. If for given theta, V and W just the right lengths, then I guess it could be. I don't know. So we can't use any Pythagorean theorem type stuff, but we can use law of cosines type stuff. Recall the law of cosines says, it's kind of like a Pythagorean theorem thing. It says the distance squared of one side plus the distance squared of another side equals the distance squared of the third side plus this additional little quantity over here. If theta were a right angle, then this would be a squared plus b squared equals c squared, if you like. Because if theta were a right angle, that cosine function would be 0, and this part would disappear. So it's actually a generalization of the Pythagorean theorem. Anyhow, I'm most impressed if you actually recall the law of cosines. It's certainly useful, but it doesn't get enough use, at least not for me, to really stick in my head. So here it is. Law of cosines says this. All right. Except we've written the lengths of the sides in terms of norms of vectors. Okay, let's take this expression. I'm actually looking for information about that angle theta, the angle between V and W. V squared, norm of V squared, we can write as sum of the squares of the components. Vector W, norm squared, we can write as a sum of the squares of the components. Vector V minus W, we can write as a sum of the squares of the components. Components of the difference would be V1 minus W1 squared plus V2 minus W2, square it, add. So expressing the norms squared, we get this kind of thing for V, W, and V minus W. Tell you what, let's leave this the way it is for right now. 2, norm V, norm W, cosine theta. So just copy that from above. Well, something happens here. We can simplify this, and out of the blue is going to come a dot product. If we take V1 minus W1, square it, we'll get V1 squared minus 2V1 VW plus W1 squared. We'll get a V1 squared and a W1 squared and a center term from FOIL. And the same with all these other terms. So there's going to be a V1 squared on both sides. There's going to be a W1 squared on both sides. V2 squared on both sides, W2 squared on both sides, and so forth. Cancel the V1 squares, cancel the W1 squares, cancel the V2 squares, cancel the W2 squares, and so forth. Then you're left with those center terms, the outer, inner, and FOIL when you do the multiplication. Remember this conversation starting right here. This is all just a conversation about numbers. Even these things are numbers. They're norms of vectors. But this is a conversation about norms. I can't say it's totally devoid of vectors, but there's no vector quantity in this equation. It's all a story about numbers. Okay, so when we FOIL these, we'll get a minus 2V1 W1 term here. Let's take that to the other side. Here it is. We'll get a minus 2 V2 W2, take it to the other side, and do that for all n terms here. So we've simplified and moved some things around. We've still got the same expression here, the 2 norm v norm w times cosine theta. And what we're going to do then is observe, hey, I factor the 2 out, we've got v1 times w1 plus v2 times w2 plus blah, 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 v sub n times w sub n. That's a dot product. So we've got on the left-hand side twice the dot product of v and w, 2 times v dot w. Let's solve for cosine theta. The 2's cancel. Divide both sides then by norm of v, norm of w, and it produces this. So cosine of theta is v dot w divided by norm of v times norm of w. I guess we could go maybe one step further if I want to talk about the angle itself. Taking that as inspiration, we'll define the angle between two non-zero vectors, v and w, as, well, I know from the picture, cosine theta equals this. So let's make theta itself, solve that for theta. If you'll let me use a cosine inverse function, we get theta equals cosine inverse, v dot w, norm v, norm w. Inspired by this. If you don't like that little inverse cosine notation, then use the arc cosine notation. So there is, by definition, the angle between two vectors, and it's totally motivated by the picture. And that's the reason we did dot products. Dot products let us talk about angles between vectors. One quick observation here, cosine inverse. What kind of angles come out of cosine inverse? I think it's probably angles between 0 and pi radians, or between 0 and 180 degrees. So keep that in mind. By our definition, we can't have an angle between two vectors, say, of negative 45 degrees. This will never be negative 45 degrees. It'll be something else. I've got a little bit of problem with a cosine function not being a one-to-one function. So the inverse function is only valid on certain regions in terms of the angles. And what we'll get out of this is angles between, say, 0 and 180 degrees. Better yet, 0 and pi. Radians, we should be speaking radians probably. Let's actually look at the computation of such a thing. Number 31 says, find the angle between these two vectors. Okay, piece of cake. I know the manipulations will be straightforward. I need to find norms of vectors and dot products. Okay, we just saw that the angle between those vectors is a cosine inverse of, in this case, the vectors are u and v, so it's u dot v divided by norm of u times norm of v. All right, let's find the norms. Vector u has components negative 1, 3, 4, negative 1, 3, 4, square them, add them together, take a square root. Let me zoom through the arithmetic a little quickly here. Gives us square root of 26. The norm of v, square the components, add them together, take a square root. Looks like we get a square root of 6 there. Yeah, I warned you a second ago. I'm going to probably see a lot of square root stuff when we do this norm stuff. Making me think, geez, we'd be awfully lucky if we can precisely evaluate that cosine inverse function. I think in this one we probably can't. Dot product, okay, let's actually compute a dot product. Haven't done one of those just yet. Take u with components negative 1, 3, 4, dot it with v with components 2, 1, negative 1, multiply corresponding components and add them together. Product of the first components plus product of the second components plus product of the third components. Do the arithmetic. Looks like we get negative 3. So we got everything we need to deal with what the angle is, and be the cosine inverse of u dot v. U dot v we just saw was negative 3. Norm of u, square root of 26. Norm of v, square root of 6. All right. If you like, can I simplify this? I can combine the square roots, I guess. 6 times 26, oh, that's 156, I suppose. Can you further simplify it? I don't think any of us know what that cosine inverse is. I'll just leave it in terms of the cosine inverse function. We could ask a calculator to give us an approximate value of that. I guess it's like 103.9 degrees to a couple of decimal places. Anything else you can do in terms of simplifying, by the way? but I'm not terribly hung up on simplifying. That's arithmetic. But I don't think there is, unless you want to rationalize a denominator, and I'm totally not into that. So we're left with this as the answer. Remember, I put the answers in a little box when that's meaningful to do. So there's the angle between those two vectors. And it's computed using dot products. Some properties now of dot products. So we introduced norms and dot products. We saw properties of norms above. Here's some properties of dot products. We'll go through the proof of one of these. Take three vectors, u, v, and w from Rn. Let R be a scalar. Then dot products are commutative. V dot w equals w dot v. Order doesn't matter. I'm not sure you've ever seen really any mathematical manipulation that's not commutative. The sophomore level linear algebra class, maybe you have. You certainly will soon if you haven't before. Matrix products are not commutative, and you've probably been exposed to matrices before, some setting. But dot products are commutative. I always think the commutativity story falls flat because most things you deal with are commutative, dot product included. We've got a distribution property. If we take u dot, the vector sum, v plus w, we can distribute. You had to have two operations for it to be called distribution. You still got two operations. You got vector addition and you've got the dot product. And this says that the dot product distributes over vector addition in this sense. If we have scalar r times a dot product, we could put that r onto vector v or put that r onto vector w. Each of these three quantities will be the same. I guess you could argue that could be called some kind of distribution. I don't know, if it was distribution, I'd expect to see the r in two places. They cleverly didn't give it a name. Yeah, at least I got two operations, scalar multiplication and dot products, but it's not behaving the way a distribution really should. So I guess it's not called distribution. We'll see something like this when we deal with matrix products later, and these guys will call it scalars pull through. They don't even call it that at this stage. We'll call it property D3. But this shouldn't be a surprising result when you think how dot products are computed. Actually, none of these should be surprising results when you think how dot products are computed. Fourth property is that v dot v is greater than or equal to 0, and the only time we get 0 for a dot product with v with itself out is when v is the 0 vector. And you know why that is? That's because the norm squared of vector v is v dot v. How would you figure out the norm? I'd take v1 squared plus v2 squared up to v sub n squared, square root of. Okay, how would you do the norm squared then? Well, I'd take v1 squared plus v2 squared up to v sub n squared. And that is the dot product of v with itself. Product of the first components, well, it'd be v1 times v1 plus product of the second components, v2 times v2. So that's where the squaring comes from. This we will make great use of. I've labeled it here, note 1.2.a. So if you see things labeled with letters like this, I did it, the book didn't, and I did it because we're going to need it later. So we'll be referring back to note 1.2.a. I can calculate norms using dot products as given here. Well, norms squared. Let's go through proof of this distribution one. Distribution of dot product over vector addition. Okay. Proof of the distribution law. All right, how do you think we're going to do it? These are vectors in Rn. Let's write them in terms of components. And then your best friend becomes the definition of vector addition and dot products. All right, so take u, v, and w, write them in terms of components as we've done so many times at this stage already. So subscripted u's, subscripted v's, subscripted w's. And let's take, say, the left-hand side of the equation and turn it into the right-hand side of the equation. It's a distribution law, eh? I know distribution holds in the real numbers. So what we're going to do, as we've done so many of these, well, the 2 or 3 that we've done, so we're going to take this question about vectors, turn it into a question involving real numbers, Hey, where's all these real numbers? They're the components of the vectors. So we'll use, I bet you, distribution on the components of something, because the components are real numbers, and we got distribution in the real number setting. All right, so take u dot v plus w, write it in terms of the vectors expressed with their components. Got parentheses here, so let's do the vector sum first. All right, add those vectors by adding component-wise, because that's the definition of vector addition. Okay, next we'll do a dot product between this vector of u's and this vector of v plus w's. Definition of dot products is multiply the first components together, multiply the second components together, and add all that stuff up. Definition of dot product. All right, let's see. Ooh, real numbers and a chance to distribute. I said components, well, I was wrong. The dot product took us out of the vector setting and put us totally in a real number setting. Okay, well, all's the better. I know u1 times v1 plus w1 equals u1 v1 plus u1 w1, because that's distribution of multiplication over addition in the real numbers. And you're familiar with the properties of the real numbers. So do the distribution in each of these. Ooh, we're dealing with a scalar. What's next? Before we go to the next slide, what should happen? Where we're going, we're trying to get u dot w plus, I'm sorry, u dot v plus u dot w on the right-hand side. Do you see a u dot v? There's a u1 v1. There's a u2 v2. And there's a u sub n v sub n. The things I over are u's times w's. Well, that's exactly what we're looking for. All right. So here's what we had on the last line, previous slide. Let's move stuff around. Let's get the UVs together and the UWs together. So all we did is use commutativity and associativity from the reals, just dealing with real numbers here. So we're good on that. And we've done this in such a way that, whoa, that's vector u dot vector w. I'm sorry, dot vector u dot vector v. And this is vector u dot vector w. The first term is u vector dot v vector. Second term is u vector dot w vector. Why is that? Definition of dot product. And then let's clean it up and write it with the little symbols with the arrows over them. And we got u dot v plus u dot w. And that was the claim. And there's distribution. And it was proved, largely like I suspected. We turned it into a question about real numbers. In the past, it was components. In this case, it wasn't components, because the dot product turned everything into scalars in a conversation about scalars. We rewrote it in terms of vectors because that was the question. But there's how you prove things at this stage. You turn them into questions about things you know. The things you know at this stage is assumed to be nothing more than properties of real numbers. All right, let's see. Another super useful definition in the future is orthogonal vectors. Two vectors, v and w, in Rn are perpendicular or orthogonal. We'll use those two words interchangeably. If I got my wits about me, not entirely something I bet on, but I'll try to use the word orthogonal a little bit more. That's more of a in-context term to refer to vectors as orthogonal. Perpendicular is a little more geometry setting than what we have. But I will use those interchangeably, hopefully with preference on orthogonal. Perpendicular vectors denoted with the little symbol you had for perpendicular lines back in geometry. V is perpendicular to W, or V is orthogonal to W. If the dot product is 0, that's their definition. Does that make any sense? What do we have with dot products? That doesn't look too useful. Here it is. Hey, if the dot product, sorry, the letters are different, but if the dot product were 0, then we'd have the cosine inverse. Numerator would be 0, so the quotient would be 0. We'd have the cosine inverse of 0. What's the cosine inverse of 0? Then 90 degrees? Pi has radians. Yeah, that's right. So it's consistent with how we had seen the geometry. I don't know if I even go further back up here. How we had seen the geometry, how we had defined angles between vectors. all that's consistent with this concept is representing a concept of perpendicular or orthogonal. Let's look at a couple of examples. All right, let's see. Question here is, find the value of x such that the vector with components x, -3, 5, is perpendicular to the vector -1, 3, 4. Now, plausibly, you could try to draw pictures for this. I mean, they're just vectors in R3. But to check for orthogonality, that sounds awfully hard to do without dot products. We got dot products, it's a piece of cake though. To make these vectors orthogonal, all you got to do is set the dot product equal to 0. Excellent. Dot products are easy to compute. You're setting it equal to 0, right? Maybe I should have pointed out that's the 0 scalar, right? Not the 0 vector. Yeah, the left-hand side, that's a scalar, ain't it? Yeah, it's a scalar. When you take dot products, you multiply components and add things together, giving you scalars. In this case, compute the dot product. It looks like we get -x plus 11. You want that dot product to be 0, take x to be 11, and that dot product will be 0. So we take x to be 11, then this vector and that vector will be orthogonal or perpendicular. Why? These are dot products, 0 then. It follows from this line right here. Another example, find a non-zero vector in R3 which is perpendicular to both vector u and vector v as given. Okay. We're going to do this in the context of this class with the stuff that we know, which will be dot products and some algebraic manipulations. If you've ever done cross products before, there's another way to do this. Well, it's probably a slightly easier way to do it as well. If you haven't done cross products, then you soon will in Calculus 3, and possibly in physics classes. Cross products come up when you do electricity and magnetism. They come up when you talk about angular momentum. Angular momentum is a cross product. Anyhow, we're going to do it the way we know is right and in the context to illustrate dot products. Okay, well, let this vector you're looking for be vector W with components W1, W2, W3. Everything's happening in R3, it looks like. We need, for perpendicular to U, we need W dot U to be 0. For perpendicular to V, we need W dot V to equal 0. Okay, let's look at those dot products. We've got the vectors expressed in terms of components. Calculate the dot products. Well, I got W1, W2s, and W3s in them. That's the thing we're looking for. And out of this, we get this for the dot product. We'll set it equal to 0 so that the dot product will be 0. W dot V, components of W, components of the second vector up there, vector V. Calculate the dot product. Here it is in terms of W1, W2, and W3. Set it equal to 0. So to have W perpendicular to U, we need this. To have W perpendicular to V, we need this. We need both of those. By the way, smart ass answer. Geez, I just take W1, W2, W3, all of them to be zeros, and we got it. Yeah, they disallowed that, though. It's true, the 0 vector is perpendicular to both of them. It's kind of uninteresting. The 0 vector is perpendicular to everything. If you think about orthogonal means the dot product is 0. Well, all dot products with a 0 vector are going to be 0. 0 vector is perpendicular to everything as a result. So they wanted a non-zero vector. Okay, so that gives us something more to do. We need to find some values of W1, W2, and W3, not only just using zeros, that make both of those equations true. We're going to deal at great length with systems of equations similar to this form. We haven't yet, so the following is going to be a little clunky, with my apologies. We'll have a cleaner way to deal with systems of equations. You should be able to follow what's about to happen, though there's some natural questions that could be asked, like, why'd you do this and not that? Well, I was just looking for a solution as one. All right, so here's the two equations we have, and we're going to do the following manipulations. Apologies for the awkwardness. It's accurate, but it is arguably uninspired. Let's take 2 times the first equation, add it to the second equation. So multiply by 2, that gives us negative 2w1 plus 6w2 plus 8w3 equals 0. And add the results. We had negative 2w1, down here we got 2w1. If I add those together, that'll give us 0 w's ones. That's why we did this. We had, what was it, 6 and 1, it'd be 7, right? 8, and it's doubled, minus 1 to give us 7 there as well. So that gives us 7w2 plus 7w3 equals 0. We could take, notice it's italicized, we could take, say, w2 equals 1 and w3 equals negative 1. If you take w2 equals 1 and w3 equals negative 1, yeah, that's going to give you 0. So that one's satisfied. If we'll plug, say, w2 equals 1 and w3 equals negative 1 back into one of these equations, let's use equation 1, so that's how it's typeset, you'll find that w1 needs to be negative 1. All right, that leaves us with just one unknown, so we can solve for w1, and we'll get w1 equals negative 1. So let's try w1 equals negative 1, w2 equals 1, and w3 equals negative 1. That'd give us this vector, negative 1, 1, negative 1. Let's see if it worked, and then go back and make some comments. Dot product of w with u. Okay, w is this thing, negative 1, 1, negative 1. Dot it with the u vector. U vector, I guess, was negative 1, 3, 4. Indeed, the dot product's 0. Check it with a v vector. 2, 1, negative 1, I guess it was. Indeed, the dot product is 0. So w really is perpendicular to both u and v, and it's not the 0 vector. Can you think of another vector that's perpendicular to both u and v? Yeah, suppose I took this vector w and multiplied it by 7. And we had negative 7, 7, negative 7. That effectively be putting a 7 on each of the components, be putting a 7 in each of these things, be multiplying each of these by 7, and multiplying 0 by 7. You'd still get a dot product of 0. If I multiply this by anything, these dot products will still be 0. Why did you choose w2 equals 1 and w3 equals negative 1? Because I like 1 and negative 1. I couldn't use zeros. If I choose w2 equals 0, I'd have to choose w3 equals 0. It's a better idea. It just doesn't work because of the type of question they asked. You want to use 4? Let's use w2 equals 4. And we'll get 28 plus 7w3 equals 0. We have to use negative 4 for w3. All right, then that'd change this to 4, this to negative 4, and it'd change w1 somehow or other. You know what would happen? I bet you'd end up getting negative 4, 4, negative 4 as the output, which is also correct. So why did I choose these particular numbers? 2 reasons. I can't use 0, and 0 is my favorite linear algebra number because arithmetic with 0 is easy, but I can't use 0. So I'll try 1. I like arithmetic with 1 as well. You want to use pi? You go right ahead. It'll work and it'll give you another vector, but I'm choosing easy numbers to get a solution. Does it make sense that there could be multiple solutions? Well, it ought to. Think about these vectors u and v living, say, let me think here. I'm going to try to give you a visual. Suppose these are vectors u and v. Excuse me. Suppose these are vectors u and v. I want something perpendicular to both of them. Well, that'd be something that points out towards you or points in the opposite direction. And the length doesn't matter. It'll still be perpendicular to both u and v. Think of u and v as lying in a plane, and vector w is perpendicular to that plane. And there's a bunch of vectors perpendicular. The perpendicular stuff gives me, in a sense, the direction. Well, I could make them unit vectors or vectors of length 2 or like vectors of length whatever. I could also multiply by negative scalars and make them point in the opposite direction. Yeah, any scalar multiple of this vector which has that geometric interpretation, would satisfy this algebra. And I like pointing to pictures when I can, and I can if we're just in 3 dimensions. So we're good to go on that. And this should make some geometric sense that we got an infinite number of possible solutions. That's a little bit of a problem when you're working these and you look in the solutions manual and your answer doesn't match identically what they have in the back. Yeah, well, it depends on the question. You may be completely correct, yet you don't get the answer that the back of the book says or that the solutions manual says. That means grading your work and grading your test can be potentially nightmarish. This question, however many of you there are out there, you could all get different answers and all be correct. So it'd be more the working of the problem that would matter than the actual numbers that come out here. Not everything is correct. There's only answers that are of a certain form that are correct, but there are infinitely many correct answers. Pragmatically, oh, that becomes a problem for grading, but you let me and my grader worry about that. And that becomes a problem when you look in the back of the book or the solutions manual. And I'll try to keep you updated on when your answer could be correct and not match the solutions manual say. Let's go back to the supplements. Let's look at this. Okay, statement is, prove that the sum of the squares of the lengths of the diagonals of a parallelogram in Rn is equal to the sum of the squares of the lengths of the sides. Okay, let's draw a picture. Here's what they're getting at. The sum of the squares of the lengths of the diagonals of a parallelogram, that's the 2 blue things here, is equal to the sum of the squares of the lengths of the sides. Okay, that's the 4 black things here. If you'll let me be so informal, these things are sometimes vectors and sometimes line segments, and they're not lengths unless I take norms. But when they talk about the diagonals, they're talking about these blue things, and when they talk about the sides, they're talking about the 4 black sides, since this is color coded. All right, and their claim is the sum of the squares of the lengths of the diagonals. So that'd be the length of this thing squared plus the length of this thing squared. The sum of the lengths of the squares of the diagonals. That'd be the norm of this vector, v minus w squared, plus the norm of this vector, v plus w squared. Norm squared, that's good. I can calculate those with dot products. It's supposed to equal the sum of the squares of the lengths of the sides. So the length of this side squared, plus the length of this side squared, plus the length of this side squared. You get the idea, squared. And those will be norms of W on this side and norms of V at the bottom and at the top. Okay, lengths of the sides are, let me list all 4 of them just for the record, norm of V again, norm of W, and norm of W again. And the lengths of the diagonals are the norms of V plus W and the norm of V minus W. Okay, we want to show this thing about squares. So we'll take these norms, square them. Claim is this thing squared plus this thing squared equals this squared plus this squared plus this squared plus this squared. Oops. Okay. Well, it's true. They wouldn't ask us to do it if it ain't true. So let's see what we can do with this. V plus W, norm of squared, plus V minus W, norm of squared. That's one side of the equation that they're claiming. The other side is norm V squared plus norm V squared plus norm W squared plus norm W squared. So I get all 4 of them. All right. Hey, how do you compute norm squares of a vector? Let's use dot products. So I know note 1.2.a, called attention to that a while ago. I know the norm of V plus W is V plus W dot V plus W. I know the norm of V minus W squared is V minus W dot V minus W. Good thing they got the squares on them. I can just treat them as dot products. If they didn't have the squares, I get square roots and it becomes a mess. All right. Hey, let's use our properties of dot products because you know stuff about dot products. There's distribution, there's commutativity. What we've used here really is Okay, we've used commutativity and distribution, but it looks like we did sort of a FOIL type thing. Yeah, FOIL holds with dot products in this setting because of the commutativity and the distribution. So we get the first dot the first, the outer, outer and last, so inner, outer. There's the inner and outers together, and there's the last. So I forget my foils. But we basically foiled on this. Same thing over here. Notice we've got negatives in front of the W, so that becomes positive. Usual type of FOIL manipulations, but with dot products this time. Okay, so, and again, it's really Theorem 1.3 that justifies that, but it's effectively FOIL. We've got norm V, we've got vector V dot vector V, vector V dot vector V. We've got two of those. Let's collect those together. Same thing with the W's. We've got two of those. Let's collect those together. Ooh. We've got 2 V dot W minus 2 V dot W. Where are we? These are just numbers, right? They're written in terms of dot products, but they're just numbers. These are all equations involving numbers. Numbers related to vectors, but there's no vector quantities anywhere in here. It's all a story of numbers. These two numbers cancel, leaving us with this. Oh, hey, norm of V dot V is the norm squared of V. W dot W is the norm squared of W. And that's what they were looking for. If you like, I can take this 2 norm V squared and 2 norm W squared and write it out as 4 pieces. So the lengths of the diagonals, the thing we started with here, equals the sums of the squares of the lengths of the 4 sides, as they stated it. That's exactly what we got out. So actually not too hard because we got to use dot products and properties of dot products. Back to the notes. Okay, got a bit more to go here. We got into this cosine theta thing and the law of cosines above. We got into that, as I said, assuming we have vectors in Rn, and that I can draw a picture. I talked about the plane of a piece of paper and then the 3 points that were involved in figure 1.24. Let's run back real quick and take a peek. Figure 1.24. Whoops, overshot it. Yeah, there we go. So we've got this point where the tails of the vectors coincide, this point at the head of vector V and this point at the head of vector W. Said something about 3 points determine a plane. That's true even in Rn. So there's some geometric assumptions under that. That is true. But let's go through and do some manipulations, but we still want to give an algebraic proof of what we're about to conclude. If I've got the cosine of theta equals to this quantity, remember cosine theta is between -1 and 1. Okay, well then this quantity must be between -1 and 1. So I get V dot W over norm V, norm W is between -1 and 1. If I'll multiply through by the norm, the denominator, the norm of V times the norm of W, we'll get negative. Norm V, norm W is less than or equal to the dot product part is less than or equal to norm V, norm W. So the 1 was here, the -1 was here, and we've cross-multiplied or multiplied through. Hey, that means we've got this dot product sandwiched between these two quantities here. This one's positive, this one's negative. Then I can draw a conclusion about the absolute value of the thing sandwiched between those. The absolute value of V dot W is less than or equal to norm V, norm W. So there's you an argument, a geometric argument, making some assumptions that we can't validly make just yet. But this is true. We're about to establish it more algebraically using properties of dot products and some unusual algebraic manipulations. But we need to give a cleaner proof other than this proof based on a picture, which is arguably valid. Arguably, this isn't a rigorous argument in terms of establishing this inequality because of that figure. You sure that's true? Well, in Rn, I am sure that's true, it turns out. But that I can't justify at this stage. So let's give an algebraic argument of this thing here. This thing here is called the Schwarz inequality. Why are you interested in this? by itself, maybe not so much in this class. Little sidebar here. Heisenberg's uncertainty principle, when couched in the right vector space, boils down to Schwarz's inequality. Schwarz's inequality in the right setting, that setting is a infinite dimensional vector space where the vectors are, never mind. But Heisenberg's uncertainty principle from quantum mechanics is related to Schwarz's inequality. So ain't that something? We're interested not so much in Schwarz's inequality, but we had a property upstairs of norms with a triangle property. We're going to use Schwarz's inequality to establish that. That's really why we're interested in Schwarz's inequality. The whole purpose in the note below of introducing Schwarz's inequality for us is to prove the triangle inequality. So let's do it. Okay, so the claim is for any vectors, v and w and Rn, the absolute value of v dot w is less than or equal to the norm of v times the norm of w. Okay, so let v and w be vectors in Rn. Tell you what, let's let R and S be any scalars, real numbers. We know that the norm of RV plus SW, norm of, is greater than or equal to 0. Hey, norms were never negative. In other words, that was positivity of the norm in Theorem 1.2. So you can't argue with the validity of this. I warned you, the following you should be able to follow. Can't say that I would have thought of some of this stuff on my own. But the proof is not too hard to follow. It's just a regular little algebraic argument. But it does have some uninspired moments, such as, why did you look at a linear combination of v and w? Because there's nothing up here involving linear combinations. Well, sit tight. It'll all come together here before it's over. So we could rewrite that as 0 is less than or equal to the norm squared of RV plus SW. I like norm squared better because I can express those as dot products, note 1.2.a. So we can take this norm squared, write it as a dot product of linear combinations. Your properties of dot products are good and nice and well behaved. So we're doing a FOIL thing here again. So we've got a FOIL type behavior so that the dot product can be rewritten like this. Remember, I ultimately want to have a conversation about v dot w. Well, I see somewhere in there v dot w, the norm of v and the norm of w. Here comes a norm of v and here comes a norm of w. So it does look promising, even though it's got these r's and s's in it, and we're going to do something with those before we're done. Okay, let's use more properties of dot product. I guess they called it homogeneity of the dot product, where they move those scalars out, get the scalars together. All right. Hey, here we've got v dot v, so we get a norm v squared here. W dot w, so we get a norm w squared here. We've got the dot product here, so we're looking good, except for these r's and these s's. Hey, those r's and s's, they could be anything, and this equation would still be true. That's the important idea. Holds for any scalars. So let's pick some particular scalars. This, never mind why they want to do this. They want to do this because it works. So that's horrible motivation. But like I said, you should be able to follow the algebra. This choice here, it hits me kind of out of the blue. Let's let R be the norm of W squared, and let S be the negative of the dot product of V and W. Okay, I told you R and S could be anything as long as they're real numbers. That's a real number, and dot products are real numbers. Negatives of dot products are real numbers. Choose those real numbers. Why? For the following reason. It works. Okay, we left off on the last slide with 0 is less than or equal to this particular linear combination. I shouldn't call it a linear combination. These aren't vectors, but quantities based on vectors. This sum. All right, and let's substitute in R equals norm of W squared. So R squared would be the norm of W to the 4th power. S we took to be the negative of v dot w. Okay, so we've got a 2. Here's that r, norm of w squared thing again. S would be negative v dot w. So we pick up a v dot w from the S. Here's another v dot w that comes from the previous line, leaving us with v dot w squared. Here we've got s squared, so we'd have s squared is this quantity squared. Of course, the negative gets absorbed, and we get v dot w squared there as well. Substitution. No problem. I could choose r and s to be anything. I choose these. Big question as to why. I'm not so much worried about why, it's just that it works out. Meaning this is a totally inappropriate type test question or something. So we get something along these lines upon substituting. And let's see, we got some cancellation here, a little bit. Here we've got negative 2, norm w squared, v dot w squared. Here we've got v dot w squared, norm w squared. We got negative 2 here, 1 here. Same type of quantities, so we're left with negative 1 of that type of quantity down here. And we can factor out what? Norm w squared. Factor out a norm w squared. It leaves us with norm w squared there from the norm w to the 4th. The norm v squared doesn't change. We still got this dot product stuff. We factored the coefficient of norm w squared out. Let's call that equation star. How y'all doing out there? Hey, look, norm w, norm v, norm w, norm v, v dot w squared and some negatives. This start equation, it involves the stuff we're interested in. So we wandered off in a weird direction, but we're getting the right type of stuff, it appears. All right. First, if w is a 0 vector, this Schwarz's inequality is going to be true. You're going to get 0 for the dot product, and you're going to get 0 on this right-hand side. And it's true that 0 is less than or equal to 0. So the thing holds if we take w to be the 0 vector. If w is not the 0 vector, then we can divide both sides of this equation by norm w squared. So if w is not 0 vector and w norm of is non-zero, then we can divide both sides by norm w squared. Usual stuff that you can't divide by 0. There's not an advanced math class out there where you're dividing by 0. They've told you stuff in the past. They told you can't take square roots and negatives. There's people living pretty normal, healthy lives taking square roots and negatives and using complex numbers. They told you can't divide by 0. Yeah, it's because you can't divide by 0. That's not a legitimate math operation. There's not an advanced math class where you're dividing by 0. You didn't divide by 0 in calculus. You did some stuff involving limits. Because you couldn't divide by 0. I mean, you wouldn't have to do all that limit stuff if you could divide by 0. Derivatives, for one thing, would be a whole different thing. You can't divide by 0. So we got to get to the little caveat of that special case. And if norm w is non-zero, we can divide both sides of this equation by that. Left-hand side stays 0. Here it is. We lose this term here, and we get this for the other side, actually written in a different order here. So we'll have norm v squared times norm w squared, right, minus v dot w squared, right, and this quantity is greater than or equal to 0. So equation star, when you divide both sides by norm w squared, becomes this. And we're almost there. Let's move some things around. Take this to the other side so that it becomes positive. Okay, so we'll get norm v dot w squared less than or equal to norm v squared, norm w squared. Remember where we're going. Got a bunch of exponents of 2 in the way. Take a square root, that'll get rid of them. Ooh, maybe introduce some absolute values. Take square roots of both. V dot w, well, we'll get the absolute value of that. Square root of something squared is the absolute value of the something. Don't forget the absolute values. Right-hand side, I guess I need absolute values there. Yeah, but remember the norms of vectors, they're never negative. So I don't need absolute values on the right-hand side. It doesn't hurt anything. Well, it's unesthetically pleasing. So don't put absolute values on the right-hand side, though it's not wrong. You got to put them on the left-hand side because for all I know, v dot w could well be negative. Dot products can be negative. And that's what we were claiming. All right, so thank you for your patience. The weirdness was the choice of R and S. Other than that, the argument you should be able to follow because it's just a little high school algebra argument. Okay, it ain't X's and Y's, it's norms and dot products and stuff, but there was no exotic manipulations in any of this stuff. Well beyond the choice of R and S. All right, so we went through that for the following reason. We want to prove the triangle inequality. We drew a picture upstairs of the triangle inequality. Claim is vectors v and w from Rn, the norm of the sum is less than or equal to the sum of the norms. Triangle inequality, it's a total piece of cake now that we got Schwarz's inequality. Schwarz's inequality was not a total piece of cake. So let's take norm of v plus w squared. That's v plus w dot v plus w. Told you I was going to use that note quite a bit. We're not even out of this section yet. Do your dot product thing. Okay. Properties of dot products tell you that you effectively can FOIL in the dot product again. Here's v dot w. I'm sorry, v dot v, which is norm v squared. Here's w dot w, norm w squared. Ooh, and here's a v dot w. But I know how big that is. V dot w is less than or equal to norm of v times the norm of w. The twos along from the right came out of FOIL. V dot w is less than or equal to norm v times norm w. That's exactly what Schwarz's inequality implies. V dot w is less than or equal to norm v times norm w. Even without the absolute values, it still holds. Right? That's the implication. If the absolute value is bounded above by this positive number, then the quantity itself certainly is. Don't be concerned with the absolute values not being present down here. We still have the implication of inequality. So we can take the v dot w and replace it with norm v, norm w, and an inequality. That's a perfect square. That's the reason we did Schwarz's inequality. To get a perfect square here, why, this is just norm v plus norm w, quantity squared. Multiply it out, FOIL's okay. Yeah, these are just numbers. They're norms of vectors, but norms of vectors are numbers. They're non-negative numbers at that. And we'll get the first squared, there you go. Twice the product, there you go. And the last one squared. So we can factor this like this. Take square roots of both sides. You'll get norm of v plus w, absolute value, yeah, but it's non-negative. And square root of this, absolute value, yeah, but it's non-negative. And I don't need the absolute values on either side here. So there's how you prove the triangle inequality using Schwarz's inequality. That would be a good test question if you were allowed to assume Schwarz's inequality. The weirdness is in Schwarz's inequality, and the weirdness, the way we proved it, comes down to that selection of R and S. This, totally unsurprising. If you let me use Schwarz's inequality, proof of the triangle inequality is very straightforward. And one final thing, let's take a look at an application. Okay, the story here, actually, let me go ahead and get a picture exposed for you. It says, the captain of a barge wishes to get to a point directly across a straight river that runs north to south. If the current flows directly downstream at 5 knots and the barge steams at 13 knots, in what direction should the captain steer the barge? All right, we don't have to worry too much about what a knot is, other than it's a unit we're using to measure, it looks like velocities. Okay, so the picture is, here's the yacht. I made this picture. He wants to go directly across. Get to a point directly across the river. So he wants to move straight across the river. We're told, let's see, that the river flows from north to south. Let's put north at the top and south at the bottom. So we get this kind of behavior on how the water flows. Let's call that vector W. And this is really just a vector sum question. So we've got 5 knots directly down. We'll write it in terms of components here shortly. He wants to go directly across. He's going to go at 13 knots. Well, if he points his boat directly across, he ain't going to go straight across. The flow of the river is going to take him downstream. So he's got to actually aim upstream in such a way that he compensates for the flow of the water to the south, downstream. Okay, so what we need to do is we need to find the velocity v of the barge. It should be a vector that points something in this direction, such that when we take that velocity of the barge plus the velocity of the water plus w, that results in this east-west vector. So that's the story, that's the picture, and that's the plan. All right, so we need to turn w into components. All right, so here's a little picture, more schematically. W vector has components, say 0, -5, it's pointing downward along the y-axis if we introduce x and y-axes. So we'll take w for water again, to have components 0 and -5 knots. U pointed horizontally, so let's give it components u sub 1 and u sub 2. Well, a second component's 0 because it points horizontally, so there is no component in the y direction, if you will. And v, what do you know about v? I know v plus w equals u. Oh, I know the magnitude of v. They told us it was 15 knots. All right, so let's take v to have components v1 and v2, usual thing. We have 2 pieces of information. We have v plus w equals u, which we can write in components as vector v plus vector w equals vector u, summing on the left-hand side. That gives us v1 plus 0, comma, v2 minus 5. Okay, that'll equal u1, comma, 0. All right, so let's see. We can tell v2 must be 5 knots just from this second component. Still some nebulosity here in the first component. I got a v1 and a u1, so we need to find, we're looking for vector v, wasn't it? We need to find v sub 1 now. We found v sub 2 is 5 knots. How are you going to find v sub 1? Well, I knew vector v had magnitude 15 knots. The norm of v, v1 squared plus v2 squared, square root of, I mean, that's the reason it's in this section and not in earlier sections, because it involves norms. V1 squared plus, well, we know v2 is 5. So we get v1 squared plus 5 squared equals 13. The units throughout are knots, not that that matters so much, as long as it's the same units throughout. I don't want unit conversion. So we get v1 squared plus 25 equals 13, square both sides. That gives us v1 squared plus 25 equals 169. Beware when you square both sides of extraneous roots. V1 squared then is 144. So we'll take V1 to be, well, plus or minus 12. There's that extraneous root. V1 equals -12 also satisfies this equation, but that hasn't going, negative x component hasn't going the wrong direction. They did set the compass directions up. So we take the positive square root in this case. The negative one is a legitimate solution. Different picture might be the one we have to take. You should be used to this from exposure to physics problems and just trigonometry problems. All right, so we'll take V1 equals to 12 knots. U1 is 12 knots as well, we discover. So we've got, we got U1 is also 12, so we get U vector is given by this. They ask us about direction. So what we have now is a distance of 12 here, a distance of 5 here, a distance of 13 here. We found the velocity vector. Let's introduce angle theta as well. Their question was, in what direction does the captain steer? So we'll describe it as an angle north of due east. Right triangle determined by u, v, and w has a cosine of theta as 12 over 13. Cosine of theta would be adjacent, was 12. Yeah, here's the vector u. velocity was 13, so we get 12 over 13. Cosine inverse of 12 over 13 is not a special angle. We'll just leave it at that. So the captain should steer the barge. Cosine inverse of 12 over 13, kind of a bland answer, but it's a correct answer. Upstream, or if you like, north of due east. So there's an application that starts with a word problem, and it falls into consideration of the norm of a vector. And you could probably have done this without all the dot product stuff, but you need to know something about norms of vectors in order to approach this one. And that takes care of section 1.2, takes care of dot products and norms of vectors. Next section, we're going to deviate a little bit away from vectors, sort of, and talk about matrices. But matrices and vectors, they just can't stay away from each other. Those will get together in pretty short order. And even in a conversation of matrices, there'll be a lot of discussion of vectors and discussion of dot products as well. I will see you in section 1.3. Bye-bye.